Right, hi everybody, I'm just going to talk to you about oxygen today. Very briefly, just an overview just in case we get a question about hypoxia. So first question is, what does oxygen do? We all know it's very important, but what does it do? So I think of the sad electron. This little old electron, it's very sad, but it likes to bond to oxygen, so I'll get to that. So oxygen is used for bioenergetics, which is a terminal electron acceptor in cellular respiration. So as the electron moves down the cascade, it eventually lands on oxygen. Biosynthetics, it's used in oxygen transferase for catecholamine productions and biodegradation. Think about oxidation reduction as the phase 1 reactions for phase 2 reactions of glucuronidation, for example. That is another role of oxygen. And antimicrobial action, so reactive oxygen used in macrophages and neutrophils. So just to summarise, SADE, synthetic functions, antimicrobial functions, degradatory functions, and energetic functions. I spelt that wrong. That's very annoying there. Anyway, hypoxia. What's the classification of hypoxia? So CASH, cytotoxic hypoxia. So the cells are unable to use oxygen, such as cyanide poisoning. Anemic hypoxia. So in other words, the oxygen level saturation itself is high enough, say 90%, 96%, but you've only got 2 grams per decilitre of hemoglobin, so you're not going to get very far with that. Anemic hypoxia. Stagnant hypoxia. So in other words, the heart is not pushing, the DO2 has dropped because the cardiac output is too low, so such as heart failure. And the classic hypoxic hypoxia. So cytotoxic, anemic, stagnant, and hypoxic hypoxia. So what's the cause of hypoxia on ITU? Well, generally it's caused by VQ mismatching. There's two broad categories of VQ mismatch. So there's dead space, and there's shunt. Dead space is caused by areas of the lung being perfused but not ventilated. Being ventilated but not perfused. So in other words, we've got the blood vessels coming around here, like this, and another one to this one, and one of these is blocked. So this becomes dead space. Okay, so that's dead space. So in other words, an area of lung is ventilated but not perfused. So all of blood goes through here. Now normally, as long as this area is not too big, oxygen level should remain satisfactory. But with shunt, what you have is, I wish I had my pen. With shunt, you've got some awful pneumonia going on in here, and so the blood still can come past, but there's no oxygen in here. No oxygen. So this causes very much drop in saturation. So this is called shunt because the blood is rushing past. So it can be worse. This dead space is more likely to be corrected by oxygen. And then there's hypoventilation hypoxia. So let's talk about how we measure how bad hypoxia is. So we talk about the AA gradient. And the AA gradient describes the difference between the alveolar oxygen partial pressure and the arterial oxygen partial pressure. So A being capital A, so that's inner gas, alveolar, A for artery. That's the difference between the alveolar partial pressure and the PaO2 in the blood. So the higher number is worse. You work out the PaO2 because you know the PiO2, which is the partial pressure of inspired oxygen, which is essentially FiO2, times the barometric pressure minus the saturated vapor pressure of water. So it's about 22 kilopascals. Then to measure the PaO2, you know the PiO2, and you take away the PaCO2 divided by the respiratory quotient, divided by 0.8. Okay. So that's to find out what the PaO2 is. So in other words, it does depend on the capital A does depend very much on the FiO2. So if the AA gradient is normal but the patient is hypoxic, alveolar hypoventilation is occurring. or the patient is breathing a low ViO2. Doesn't really make sense. So if the gradient is raised, then there's usually a diffusional defect, such as pneumonia. We also use the PaO2 to FiO2 ratio, which is very much used in classification of ARDS. So mild ARDS is 300, moderate is 200, and severe is 100, or 40, 27 and 14. That's hard to remember. So I do remember the millimetres of mercury, even though being British we do tend to use the kilopascals. Talk about the oxygen dissociation curve briefly. So the P50 of the oxygen dissociation curve is where the oxygen is 50% saturated, and that's normally at a PaO2 100. God, I wish I had my pen. That's normally at a PaO2 of 3.5. So if the oxygen dissociation curve shifts to the right, it means that oxygen has less affinity for the haemoglobin, and so a higher kPa is required to reach 50%. But it also means that the haemoglobin will give up the oxygen at hypoxic levels at the cellular level, and that can be caused by CO2, increased 2,3-DPG, increased acidosis, and a high temperature. If you go left, it means the haemoglobin has a higher affinity for oxygen, and the most relevant here is that reduced 2,3-DPG levels, because 2,3-DPG is used as a red cell metabolite, and so in stored blood, the 2,3-DPG levels drop. So the oxygen dissociation curve shifts towards the left. In other words, the haemoglobin has a higher affinity and it's less likely to give up its oxygen. That's why transfused blood takes a couple of days really to make a big difference. Right, okay, so we're going to talk about oxygen delivery, and what we do to work out oxygen delivery is we first of all work out the oxygen content, which simply means that we times the saturation times the haemoglobin, which is in grams per deciliter, times 1.34, and then add the amount of dissolved oxygen, which is not relevant at normal atmospheric pressure. This is why a hyperbaric chamber will work, because it increases this proportion by increasing the PaO2 such that this 0.023 becomes less relevant. Well, by massively increasing the PaO2, you compensate for the fact that you only dissolve a very small amount of oxygen actually into the blood. So then to work out the oxygen delivery, you take the content of the oxygen content in the blood, which is in mils per 100 ml normally, times it by 10 to get mils per litre, and then times that by your cardiac output. And normally arterial oxygen content is around 20 mils per 100 mils, and normal venous oxygen content is 15 mils per 100 mils. So the oxygen content then therefore is 5 mils per 100 mils. Sorry, oxygen consumption even is 5 mils per 100 mils times the cardiac output times 10. So it's 250 mils a minute. We know that because that's what the minimum gas flow rate on an anaesthetic machine can be. We measure the oxygen content using the pulse ox. Uses Beer-Lambert principle, which is that the absorption of infrared light is proportional to the distance that it travels. So in other words, the greater the distance, the greater the absorption. And something else, which I can't remember. The pulse ox uses these two frequencies of infrared and red light, and because that's where the difference between saturated and unsaturated haemoglobin is greatest. It's less accurate, less than 80%, and it can be inaccurate with carboxy, metheme, and sulfhemoglobin. Just a brief conversation about venous oxygen levels. So you can true mixed venous is measured at the distal port of a PA catheter. So that's in the pulmonary arteries. Normally it's greater than 70%. A low level indicates low cardiac output or high tissue uptake, so hypermetabolic or low cardiac output states. If it's normal, it doesn't mean all's well. Central venous roughly approximates to mixed venous, but that's taken from obviously a central venous catheter. And again, 70% is normal. Has been used in early goal-directed therapy, and Rivers used it, but other studies obviously have subsequently done this and found no difference at all.